Hi, hello. Hope everybody's well. Okay, so today you can see I'd like to work through questions 18, 19, and part of 20. I'm going to ask you for homework to do 18B and also 20B, so I'll be working the ones around that. So let me start in. So let's see, I want to start off with question 18A here. The general question says D is the domain and C is the codomain in their finite sets. In this case, prove that if there's a correspondence between D and C, then the two sets have the same number of elements. And the hint is for each of them you can do induction on either the number of elements in C or else the number of elements in D. So I'm going to, it so happens, do induction on the number of elements in C. So for, let's see, 18A, it says if f is 1 to 1, then the number of elements in C is greater than or equal to the number of elements in D. B says if f is onto, that's the one you're going to try for homework. If f is onto, then the number of elements in C is less than or equal to the number of elements in D. So if f is both 1 to 1 and onto, that is to say if f is a correspondence, then of course the two sizes are the same, that the size of the set C and the size of the set D are the same. So I'm going to have a whack at A, and I'm going to do, as the hint suggests, I'm going to do induction, and I happen to choose induction on the size of C. Okay, so let me click this out here, and I'm just going to do it on a piece of paper. So let's see here. So I'm going to assume that f is 1 to 1. Oops. So I'm going to assume f is 1 to 1. And I'm going to do induction on the number of elements in C. So the base case is that the number of elements in C is 0. So since the number of elements in C is 0, and the function associates inputs with outputs, there are no outputs, there can't be any inputs either. So in this case, the number of elements in D is also 0. If there are no outputs, then there can't be any inputs to associate with. So f is the empty function between the empty set and the empty set, and it's not a very interesting function, but anyway, that's the only case that happens here. Okay, so that's the base case is done here. The size of C is greater than or equal to the size of D, as needed, as required. Okay, so that was a trivial case, so often happens with the base case. All right, now for the inductive step, for the inductive case, take the statement to be true for the cases size of C equals 0, size of C equals 1, all the way up to size of C equals n. And you consider the next case. Okay, and as so often happens with induction, there's almost like a formula to get you started, but then at some point you got to do something at some point, and so that point is now. There's a number of ways to do the problem and all that kind of stuff, but to me, the sort of thing a person would do is to draw some pictures, and when you draw pictures, it seems to me there are two possible pictures. Now the pictures of course don't form part of the proof, but nonetheless there are two possible pictures. In one picture, you have a domain and a codomain and arrows between them. And for every arrow in the domain there's an arrow in the codomain. And they line up in a one-to-one way. And then the codomain either has extra elements in it or else it doesn't. So to my mind, when you start drawing some pictures, you see that there are two cases like that, and that suggests where to go with it. So there are two cases. So you notice, just as an aside, you notice that I say there are two cases. I don't say something like one way to do the problem, or one way we can proceed. I say there are two cases, and of course there are other ways to do the problem that don't involve two cases, perhaps. But anyway, in the way we're doing the problem, there are two cases. So the first case is that there is an element of D that it's going to be an element of C that is not mapped to. So the first case, that there is some C hat in capital C for which there is no D. With f of D equals C hat. So C hat is not at the end of an arrow. Now, end of an arrow is not a defined mathematical term, so I wrote it in defined mathematical terms. But anyway, C hat is not at the end of an arrow. Well, if C hat's not at the end of an arrow, then we can omit it, and that's always the way you do induction, right? You always find some way to get rid of something and fall back to the prior case. So if C hat is not at the end of the arrow, then we can omit it, and the picture's exactly the same. The function part of the picture is exactly the same. Then C hat is, I'm going to call that C, take away little c hat, is such that the restriction of f to D and C hat given by f hat of D equals f of D is again a one-to-one function. Because there is no D mapping to C hat, so if we just take our eraser and erase C hat, the picture is exactly the same, so the function must still be one-to-one, and thus the size of C hat greater than or equal to the size of D. But wait a minute, we already know that the size of C is greater than the size of C hat as required. Okay, so that was the first case. That was the first of the two cases, and again, when I was thinking about how to do this, I thinking of pictures, drew a couple pictures, tried. Oh wait, there are two cases, and so that case seemed to me to match, to make sense. Okay, next up is the other case. The other case is that there are no extra elements. So the second case that for all C in capital C, there is a D in capital D, where f of D equals C. There are no leftover elements, there are no extra elements. Every element in capital C, every element in the codomain is the end of an arrow. Okay, what to do? Well, always in induction, what you do is you always try to drop out that extra one and fall back to the prior case. Sometimes you fall back a couple cases back. We've seen that happen. But often you fall back to the immediate prior case. So my idea here is to pick a particular element of capital C, erase it, and erase the associated D. Fix some C hat in capital C, and also fix D hat in capital D with f of D hat equals C hat. Find the D that maps to C hat. Oh, but I only wrote one. Aha, but the function is one-to-one, so there's only one such D. Is only one such element of D because f is one-to-one. That's the key observation. That turned out to be the part that a person has to scratch their head about a little bit. Okay, so when you erase that C hat from C, thinking induction, how induction always works, you got to cross something off and then cross the associated thing off, and what's left now will be a one-to-one function. But how do I know I'm only crossing off one? I'm only crossing off one because the function's one-to-one. That's what makes it work. Okay, then F hat map D hat to C hat is one-to-one, where D hat is D take away little d hat, and C hat is C take away little c hat. Because all we did was erase one arrow and the thing that begins it and the thing that ends it. So if the function was one-to-one before, it's one-to-one now. Okay. Thus, I'm looking at the size of D hat. I guess I'm going to write D hat. I like D hat on the left. D hat less than or equal to the size of C hat by the inductive hypothesis, because they each have one element fewer. In particular, this guy here has one element fewer, so we fall back to the inductive hypothesis. That is less than size of C. Okay. And in fact, I can conclude so size of D, which is size of D hat plus 1, since this says strictly less, must be less than or equal to the size of C. This says strictly less, so it's at least one bigger. So if you add 1 to this, you get to less than or equal to. That's what I did, so I'm done. Okay, so that was a little tricky. I don't think that we've had induction arguments that were that tricky. Of course, each individual part is not necessarily tricky, but when trying to think about this problem, how do you do this problem, I have to admit, I spent a couple minutes going what to do. And of course, you might very well come up with a slightly different way to do it, maybe a vastly different way to do it. But in this case, I'll at least say that the induction part, the base case, the inductive step, all a person says, okay, well, I have some idea of the skeleton. Then you say to yourself something like, well, usually you want to fall back to the prior case. So I'll grab some element of C and I'll see what happens when I omit it, hoping to fall back to the prior case. And there prove to be two ways you can omit the element. One way you can omit the element is if it is the end of an arrow. That was a little harder to say, but okay. If it is the end of an arrow, then you have to omit the D that begins that arrow. On the other hand, if it is not the end of the arrow, you can just cross it off and the picture is basically unchanged. Okay, so a larger induction argument, I didn't get it all on the screen here, a larger induction argument than we've seen before. Maybe I think this might be the longest induction argument we've seen so far in the course, and a somewhat more intricate induction argument, but not brutal. Just simply person, if you walk around for a while thinking how to do, and of course when you get it, of course, it's tremendously satisfying. That's part of the fun of mathematics, is when boom, you go, I got it, I've been working on it for a while, I got it, that's great. Go have soda, kind of thing. Okay, so good stuff. Here we are. I'm looking at 3.18. I did 3.18a, and I mentioned I'm going to ask you to do 3.18b, and you don't have to be all that perceptive to figure out that although it's not exactly the same, it's at least a lot the same. You can do it by induction on the number of elements in D. That you could, absolutely could. I tried writing that down and I got it to go. But you can also do it by induction on the number of elements in C. And so if you're following along what I did in the prior one, you might give that one a try first. Okay, next up is the pigeonhole principle. Turns out that that one hint, one suggestion that something is often used is when it has a name. So if we call something Euclid's lemma, for example, that often means that's often a suggestion that it's something people refer to all the time because they need to refer to it all the time, which is why they gave it a name. So this fella has a name, so that's a little bit of alarm in your head that this is something that is going to come up. You're going to see this sometimes in surprising places, and you do see the pigeonhole principle sometimes in surprising places. Okay, here we go. Suppose that you have more than 0 many pigeonholes. You know, those old desks with all the little holes in it, and you put pieces of paper in, you know, next Wednesday I gotta do this kind of thing. So you have more than 0 many pigeonholes and more than n many papers. So you have n many pigeonholes and more than n many papers. Then at least one hole gets at least 2 papers. So you have more than n many holes. Excuse me, you have n many holes, I misspoke, sorry, you have n many holes and more than n many papers. So you might have 12 holes and 14 papers. When you finish shoving all the papers into holes, at least one hole gets at least 2 papers. Now, one hole might get all 14. That could happen. But at least one hole gets at least 2 papers. Okay? It just turns out that's a principle that comes up a lot in practice, seems to appear in the darndest places sometimes, and it has a fun name. Okay, so the idea is really very simple. If all the holes were to get at most one sheet of paper, then you have a function associating a paper with its hole. That function would be 1-to-1. But by the prior exercise, the one we just walked through, the longish induction argument, by the prior exercise, the number of holes would be less than or equal to the number of papers. The domain has less than or equal to the number of elements, it's the codomain. But of course the condition here is the opposite, it's that the number of papers exceeds the number of holes, so it can't be the case that you have a 1-to-1 function. So maybe it's 2-to-1 or 3-to-1, 4-to-1, but anyway, it's not 1-to-1. Okay. So that's an immediate application of the prior result. Might have seemed a little bit abstract about 1-to-1 functions and codomains and domain, but it proves to be the case. Don't want to say everything's important, everything's critical. If a person doesn't know this, they might as well not be getting out of bed in the morning. That's of course not right. But 1-to-1 and onto is one of the big themes in mathematics. It's one of the big things where a person, a mathematically trained person, uses to organize the world. So it's one of the things that I have found sort of going through, not just in math, but also doing a lot of computers. It's one of the things that I have found where you say to yourself, you know, this is really, comes up all the time. Okay. Anyway, so that's the pigeonhole principle. So let me move on to exercise 20, and I'm going to do A and C because I'm going to ask you to do B. You'll see that A says 1-to-1 and B says onto. So this is something like 18, where I'm asking you to do something that isn't exactly the same as what I did, but it's at least closely related. A person might get a good idea, a sort of bootstrap way to start. Okay, so in short, it says a composition of 1-to-1 functions is 1-to-1. So let me bring up the paper here, and there we go. Okay, get rid of the paper I was just using a minute ago. A composition of 1-to-1 functions is 1-to-1, and I was a little bit afraid when I was thinking about this that it might seem kind of abstract. So let me give it a whack, and we'll see how we do for a picture. Now, of course, a picture isn't a proof, but it helps a person get started. So I'm going to draw two 1-to-1 functions. Okay, I have a domain and a codomain, and then I'm out of letters, so I got to use B or some other letter over there. 1-to-1 function means never do two arrowheads go to the same dot. So never do two arrowheads go to the same dot. Okay, there can be dots left over. That can happen. That can absolutely happen for 1-to-1, but never do two arrowheads go to the same dot. Okay. I won't make the arrows cross or anything. That just makes the picture more complicated. Already I have a tough time with graphics. There we go. Okay, so this is a first 1-to-1 function. Here's a second 1-to-1 function. So I'll call the first one F because I'm not a very imaginative person, and I'll call this one G. You notice that this dot here is in some sense irrelevant. because you go over and you go over, you entirely ignore that dot. All right, okay. Still, this is a one-to-one function. Never do two arrowheads go to the same dot. And this is a one-to-one function. Never do two arrowheads go to the same dot. And when you take the composition, I don't know, I don't have colors. Never do two arrowheads go to the same. See what I meant what I said about being terrible with graphics. Never do two arrowheads go to the same dot. Never do they. There's no kind of collapsing. There's no collapsing at the first stage. There's no collapsing at the second stage. Never do two arrowheads go to the same dot. Okay. Okay, ready for a proof. And the thing about the proof is going to be that I'm not going to say something like there's no collapsing. Instead, I'm going to follow the general pattern for how you make arguments about one-to-one functions. So I talked about the general pattern, and I'm going to follow it here. So for assume, oh, I forgot to say proof. Assume F mapping D to C and G mapping C to B are one-to-one. And consider, don't say F circle G, don't say, don't say F circle G. How many hundreds of times have I said that? Instead, consider it's G circle F. Because G comes after F. I know it's peculiar, but it gets written over there. And that, of course, starts here with D and ends with B. Okay, so the way you show that a function is one-to-one is you assume that it goes, that two inputs go to the same output. Little d. Can you read that? G circle f of d1 equals G circle f of d2. And then at some point this person's got to do some thinking, of course. But the conclusion is going to be then d1 equals d2. That'll end the proof. Okay, so this is very standard way to prove that something is one-to-one when I have to show that something is one-to-one, and I've mentioned that that's something I find myself doing all the time, not just in computers. This can be not just in math, but also in computers and a lot of other areas in life. To show that something is one-to-one, you always want to start by assuming you have two things go to the same place and conclude they must have been the same thing. Okay. All right, let's see how I do. At some point, you have to do some thinking. Okay, so I think G circle f of d1 is G of f of d1. I put in a little extra space just because I don't know. Equals G of f of d2. If I was writing it in LaTeX, I probably wouldn't put that in. But this says G of something equals G of something. G of two inputs equals the same output. G of two inputs equals the same output. So because G is one-to-one, that tells you that the inputs are the same. Because G is one-to-one, f of d1 equals f of d2. One-to-one function, exactly it's not the most conceptually clear way to express one-to-one, but property of one-to-one is that if the outputs are the same, then the inputs are the same. Okay, so the same output, it says right there, same output. I supposed it. It says right there, same output, so the inputs must be the same. And now a person sees, well, but that's true for f also. Sure it is, sure it is. Because f is one-to-one. I never leave the right amount of space. Because f is one-to-one, we conclude that d1 equals d2, and we're done. Okay, so the composition of one-to-one functions is one-to-one. In this picture, though, I didn't say something like arrows. I didn't say any such thing. I didn't say collapse or you don't lose any information. I didn't say any such thing. I instead went through the standard way of proving things are one-to-one in this case, or for the one I'm going to ask you for homework, I suggest you try the standard way of proving things are onto. Okay, and we talked about that in the last video. Okay, let me bring back my window. There we go. So if G circle F is 1 to 1, then F is 1 to 1. Oops. Right, so I just did that a composition of 1 to 1 functions is 1 to 1. Now what I want to do is if G circle F is 1 to 1, then F is 1 to 1. So of course I'm going to do I have enough room? I'll just turn the paper upside down. Okay, so let me click out of here. This stupid thing. Here we go. There we go. Just turn the paper upside down. I don't need a new piece of paper. Okay, so I'm supposed to assume here, I'm supposed to assume that G circle F is 1 to 1, and I'm supposed to go on to prove that F is 1 to 1. So I got to start off by saying assume G circle F is 1 to 1. Oh, my handwriting is deteriorating. Assume G, which doesn't that far go. Assume G circle F is 1 to 1. Okay, and I want to show that F is 1 to 1, and of course a typical way to show that something is 1 to 1 is by contradiction. So I'm going to argue by contradiction. It's not the only way you can do it. I could have lots of other ways to do it, but I happen to choosing to do it by contradiction. So I'm going to suppose for contradiction that F is not 1 to 1. Okay, and I think it's polite. I think it's helpful to write something like for contradiction, because a person who's reading your argument wants to know why are we doing? Well, oh, we're going to get a contradiction. Okay, F is not 1 to 1. Then there are a D1 and D2, so that F of D1 equals F of D2. And D1 is not equal to D2. That's what it means to be not 1 to 1. That there are two inputs that go to the same output. But then G of F of D1, G of F of D1 equals G of F of D2. And so G would be, and so G circle F would be not 1 to 1. Contradicting that, G circle F is 1 to 1. Okay? There are other ways to do it, but sometimes contradiction is sometimes contradiction is a good choice. Okay, and I do think that assuming F of D1 equals F of D2 immediately, of course. Okay, very good. Okay, let me bring back the sheet again, just to remind a person. So I'm asking you to hand in. I will be asking you to hand in. It is part B of 18 and then part B of 20. And again, just point out one more time is that in the A part I did 1 to 1, and I'm leaving you to think about onto. And in the A part I did 1 to 1, and I'm leaving you to think about onto. And it doesn't mean the only way to do these problems is by doing them in a way that is at least somewhat like the A part, but it gives a person a leg up. Okay, very good. So that's the next section, and again, hope everybody is well, and hope you had a nice Easter holiday. Okay, bye bye.